Good afternoon. Welcome to lecture 63 and 64 on thermodynamics of materials. Today we will discuss effect of temperature and pressure on equilibrium constant and equilibrium composition. So topic is effect of temperature and pressure on equilibrium constant. Namely, I will tell you K, the one that we know, or Kx. Today I will introduce Kx. First, this is the effect of temperature and pressure, P for pressure. And you can write Gibbs-Helmholtz equation. Helmholtz equation, Van 't Hoff equation. Okay, this will be, let's start with this. Let us consider G is H minus Ts, or Tg is, if you recall, is actually I'm just quickly writing down this to just refresh you. TdS minus SDT, and if you recall this, du plus PdV plus VdP, just accommodating all steps, VdP minus TdS minus SDT. Recall, this gives you U is du plus dW is TdS, leaving behind VdP, the famous dG is VdP minus SDT, or right here. So, or continue, del G, what is this? This is del G by del T at constant pressure is what? Minus S, negative entropy. Or still, now go back to this, or G is H minus Ts is what? H minus plus T del G del T at constant pressure. Dividing by T square, or G by T square is H by T square plus 1 by T del G del T at constant pressure. Or what you see, or I'm writing this way, you follow me. 1 by T del G del T at constant pressure, just side change, minus G by T square is minus H by T square, just side change. This is actually or this, as I write here, I can write, you note here, this fixed mass systems, which type of system I am talking? G is H minus Ts. This line applicable to what system? What? The fixed mass, fixed composition. Example, 1 mole of ideal gas. That I have started with that. So system with fixed mass and fixed composition. So far, I have considered. Okay. Okay, good. That is so. This, or I'm writing this. We follow del okay, del G by T. You just check this del T at constant pressure. You check this minus H by T square. Left hand side, very easy to follow. See, in parts G by T. Okay, 1 by T. First differentiation by parts. Okay, and ddt of 1 by t is minus g by 1 by t square, so minus g by t square. Good. So this you can write, this is actually you can write this is your basic Gibbs-Helmholtz equation. This is your Gibbs-Helmholtz starting. I'll give you number of them. The beginning you try to follow just couple of steps and Gibbs-Helmholtz. Gibbs-Helmholtz equation. Alternative form, alternative, that is also useful. Alternatively, that you know, alternatively noting that d 1 by t is minus dt by t square. You accept this, d 1 by t is minus dt by t square. Apply that. If you apply that, you get this d g by t. D means del. I should write del 1 by t at constant pressure is just h. This is also h. You can check this. Apply this minus dt by dt goes the other side. Dt by t square is d1 by t, and d1 by t comes this side is h actually. Minus is absorbed there. Minus there. You check this. It's very easy. So this is also alternatively. Always I will use these two alternatives. Okay. On another occasions also. So just happy. This is also Gibbs-Helmholtz. Alternative. So Gibbs-Helmholtz equation. Note this. Now again I write applicable for, as I already said. Okay. So applies to fixed mass fixed composition, fixed mass fixed composition system. Also I am writing Eg 1 mole oxygen, that is a given species. One species, a single species. I'm sorry, very sorry, a single species. Yes, sorry. A single species. As different from this is what? Other type of system. What is that system? Species. Yes, but spelling is okay. Single species. Okay. For chemical reaction system, now tell me. Now for a chemical reaction system involving a number of species, reactants and products, which is also known as what? Chemical reaction system which is involving a number of, this you know, this trick you know, Kirchhoff's equation, all discussed, involving a number of species. Obviously, they are called reactants and products. That is a tell me, system with okay, formally is known as system with variable mass. Tell me what I said. Chemical reaction system is variable mass and or with or without. With or without, tell me what? With or without variable mass, with or without variable composition. This is chemical reaction system. Solution system also, this I said, system with variable mass, with system of system with is not system of So these chemicals, what change you will make it? Tell me. Same. Recall Karpov's equation. Single species, chemical reaction. Number of species, reactant products. This will be delta. Chemical reaction delta. Just these three. Delta, delta. Over for chemical reaction. So that will write. So that will be actually our goal. Del G by T, that will be pertinent for chemical reaction. Delta G of a chemical reaction under constant pressure is right minus delta. It is forever applicable. Don't ever forget this trick. You start from a given species and you are going to apply for chemical reactions. What is this delta? Can you tell me? Delta G is what? G product minus G product is a species, apply. G reactant is a species, apply, and subtract. Obviously, you get this. The other side will be also H product minus HB and delta H. So, or alternatively both. So box this. By all means, box this. This is your Gibbs-Helmholtz. Alternatively, you write yourself del G by T. Stop here. Over del 1 by T. Is it right? This one. Next, the other one. Del 1 by T under constant pressure is tell me delta H. Delta H is delta H. This is right. These two are, I can box this. These two also gives Helmholtz equations. So many forms. First form, this is for a species, this is for a chemical. Gives Helmholtz. Okay, you just save this. Then I move to the next one. Acha, this is actually a table. Oh, sorry. Acha. Now I tell you what is this? I tell you what, I write here, okay, I'm writing here, okay. Once more, just for some clarification, once more, I'm writing this one. Del, actually, by the way, if you ask an alternative definition of enthalpy, you can define this. What is enthalpy? You have seen, you have read enthalpy. H is U plus PV, basic, formative one. H is U plus PV, U energy plus PV energy. This is also actually how you can get this, the derivative of G by T against 1 by T under constant pressure. Also, another thing I will add here, this you follow. This is actually very well. This needs some discussion, but once removed, forever removed. Mental block. Delta G by T by del T, constant pressure. This is I am writing here, constant pressure, also composition. This may be confusing, but not confusing at all. Is minus delta H by T square Gibbs-Helmholtz. This time I am writing GH equation. That's right. Gibbs-Helmholtz, not bad. Gibbs-Helmholtz equation. Once more. So I have added composition. Why they follow this? What does it mean? See what is the business here, sir? What is why these so many equations and what you are doing, sir? So I want to tell you this. Hey, one thing I have made a mistake. Have you? Delta G by T. This is also D1 by T. So one thing I tell you, you follow composition. It was actually initially fixed mass fixed composition. Here also composition. Effect of temperature only, pressure and other things which may influence. Please don't allow to change. So composition changes free energy. Free energy is very dependent on composition. Free energy, partial molar free energy, product free energy, reactant free energy, means activity. So his free energy is a function of activity, GI bar. So so composition should be, so I want to study only the effect of temperature. What does it mean? You refer to this. Why now conflict is, you suddenly saw variable composition. When you blindly study, you never reach the truth. Never. This so variable composition actually, this significance of this I tell you. How to, this involves what? G is a function of, tell me, temperature, pressure, Ni, Nj, Nk. This way it allows you to write. So this is, see, variable mass. Follow me. And follow me. I already discussed variable mass. You can take any, this is an independent variable. Take any temperature system, any pressure system, at any Ni. Say CO gas, O2 gas, CO2 gas. Any, and then what will happen as you take, so variable mass, moles means mass, and composition is for mole fraction. Obviously, mole fraction. I'm choosing any mole fraction. So variable mass and variable composition. Sometimes it can be without variable composition. This also discussed, but actually coming after break, long break. So metal plus oxygen and metal oxide, the reaction NM, NO2, NMO2. So you have any amount N, any amount oxygen, any amount MO2. So applicable chemical reaction. But this is example of without variable composition. Why, sir? Because they don't enter into any solution. M is pure, MO2 is likewise pure, O2 doesn't mix with this metal and metal oxide. First one, CO gas, O2 gas, CO2 gas. For the reaction, CO plus half O2 is CO2. So they all gases are miscible in all proportions. They make actual mole fraction. So okay, they mix up, and so their composition is no more the same, no more pure. Impure, they have become impure. Metal remains metal, pure metal. Second case, metal. So with or without. Okay. Chemical reaction. So short chemical reactions are chemical reaction system. This is, sir, a given species, 1 mole of oxygen systems. So these are the things, sir. Now, so variable composition means, hey, this is the meaning. So I am writing here different thing. So then what are you writing? I tell you what, I am studying the effect of temperature and pressure one by one. When I study effect of temperature, means I should actually keep pressure fixed. Otherwise, what I am doing? This is the concept of partial derivative. That keep the other variable fixed. So that I am doing. Composition also, obviously everyone knows delta G is a function of composition, is activity delta G. So G is a GI bar is GI0 plus arctel and I. So all these things. Now how to correlate this? You follow this. Most of the things are mental block. Otherwise, memorizing things. So that's why this is the trouble. I tell you, this figure you refer, what I am telling, you will very easily follow. That figure, famous figure. G prime, recall, T, P, free energy minimization curve versus N. I am not elaborating on this. What I am focusing on this is the equilibrium. What does delta G is what? Follow. As write here quickly. Though I have written here, but once more write this to show the minimization is this equilibrium. This I am not going to discuss. What I am saying, what is the delta G, sir? Remember I told you, at a delta G at this state, at any state, delta G at this state particularly. Delta G refers to this state. Delta G at any state, not state change. Any state. If it is change of state, then what it would be? Delta G prime Tp. G prime Tp, state 1, G prime Tp, next state 2. That is delta G prime Tp. But this is delta G. Means at a state there is product reactant and partial molar energy difference. So at any state, in this state. So now what is the significance of this? So I'm studying the effect of temperature. So temperature is, you change the temperature, don't change pressure. So don't and composition, what is the meaning? Say, sir, this is the composition. Don't change this composition. Don't change this pressure. Change the temperature T1, T2 and see what happens to delta G. The delta G changes with temperature, keeping pressure at this composition, not this. Don't take this. No, this. This is the significance of this subscripted composition. So this pure delta G, how it is changed? If I change to T1 to T2 is like this. So composition, this is the same composition, right? Same composition, right? Same composition, and you write here, change here. Shall I write here? Same pressure. I don't allow them to change. What I'm changing here? Tell me this. T, right? Nicely. So T1 once. Draw a curve. Draw this curve. T1. Change T2. Again draw. Again draw. Again draw. Then you will see how this delta G value will change. T1, T2, T3, so on. This is the significance of this. Nothing else. You follow this. I am applying where delta G is. I am applying the delta G of this value. So you may ask, sir, will this curve remain same as we change the temperature from T1 to T2 to T3? They will change. They will change because delta G will change. Delta G is actually, delta G is product minus reactant. Delta G is what? G product minus G reactant. Never forget this. Delta G. So at a state, how you get delta? Recall, at a state, how can you ever get a delta? Delta refers to state 1 to state 2. But at a state possible, the G of product minus G of reactants. I may write here. Recall, what is the delta G? G product, sigma actually. Product minus sigma G. I can remove this, na? This I can remove at least. This sigma G. Recall this. I tell you, this GI bar, so-called GI bar. So GI bar is GI0 RTL. If you may actually unnecessary, okay? A function of temperature. So you are changing the temperature. So right, in case you are interested, GI bar. This is a G product means GI bar is GI0 plus RTL and temperature will changing. So GI bar changing. So delta G changing as a whole, and new values are coming. What is that change? Reflected by this. Over, very interesting. Now, if you understand, nothing like that, okay? This you have understood. If the reactants and products are at standard state, right? If the reactants and products, when the reactants and products are at standard state, quickly. Standard states, what you write? Delta G will be replaced by delta G0. So I write let me write delta G0 by T over del T under constant pressure composition. You maintain this. So I tell you what, why I am giving this will go up to in the solution thermodynamics also. This nature, this will follow. So you never be fooled, or you never be tricked, or you never feel uneasy about this. And follow this. One thing, sir. This you follow from me. That this, sir. This one delta G. How that it is governed by pressure, governed by composition, no, and temperature. This time currently studying the effect of temperature. You might say topic is pressure come later. Then I will not change the temperature. Very easy, very systematic, logical. So this is what right hand side is what? Tell me. Corresponding all. When you do, see, when you G, I am H. Left hand side is G, right hand side H. Left hand side delta G, right hand side delta H. Is GI bar M, HI bar M, delta GM, delta HM. Just go this way. Okay. I'm saying actually these are coming later on to solution more minus T by T square. This is very interesting, huh? Now I tell you what, since now can I remove all these things? These are not required at all. This over. Okay. So this you remove this. Clumsy. Oh yeah, actually it is better to use hand rather than this. Okay. Now at standard since for standard states, what is your idea? It is better ask answer like that. Interactive class. So pressure constant is very important. For standard state is what? But by defined by 1 atmosphere. So what's the question of constants? Where is the scope of change in pressure? So it is redundant. I will remove that. So see, standard states actually pressure is P is specified fixed at 1 atmosphere. So and composition is also pure. Composition is pure substance. So composition is actually there is no scope of composition changes. Okay, say mole fraction changes, and pure state 1 atmosphere, P specified at 1 atmosphere, and pure state considered. Pure states considered. So the logic is so constraints. So so the two constraints and the above two constraints, pressure composition are are not required, are not applicable. So I'm writing the moment constant is not there, partial derivative will be total derivative. D will be bent to particle. So that actually you reach. No, nothing. Noting delta G0 is what? Tell me, equilibrium constant. What is the relation? Delta G0 is minus RT ln K forever. Thermodynamics means, in a sense, that relation. Thermodynamics problem solving is delta G0 is minus RT ln K. So minus RT. One thing I tell you, just maybe informally, these steps, how to reach this. It is actually written somewhere and then it is written here. And this figure is not meant this. In most cases, teacher, books, textbooks, classical books, how it is coming here. So since if I consider standard, even can I should not name this. If you consider this. Consideration of this, why these are moved out and why they disappear and why they are actually included. So these are the important points. This is how you master the subject. You will be very confident, then you will be able to teach others confidently. That is the whole issue. And you can apply in your research, in your teaching, apply confidently. See, I have confidence. You may see this. So that's why you have no. If you show me any book, I will counter. Even you will not see any book. These steps you will never see. This whole thing starting from this year, you see why these are out and why in actually who said composition and what composition, what is the chemical reaction composition is changing. How do you write this? And many don't write at all to avoid this any trouble. Don't write at all. But if you see, this is actually okay required. So this is clarification. So now what is this? D dt minus R10 d dt. I'm writing d dt. Now I'm asking you why it should be. Can you give a box there? It's very important. It's okay though. First of all, it's okay though. What I've written? It's very easy. Substitute and do this. It's okay. You see, minus cancel is okay. Very easy. Very easy. When it is difficult, I will let you know. Let me skip when it is very easy. Alternatively, let us see. Alternatively, this is right. I write this. Alternative. I taught you how to write alternatively, right? Always remove all this. In fact, you see here. Alternatively how to write. Tell me alternatively. So somehow I have to come down to this. Tell me, is it 1 by t square dt, d1 by t. dt will be d1 by t. So d ln k d 1 by t is minus delta minus. You get a minus, no? dt of 1 by t minus dt by t square. So remember I wrote somewhere, yeah, you take a look. dt of 1 by t, shall I write you? I wrote once, time is actually not wasted. Yeah, consume. This is okay. So this I can box this. This will be what? Mentor. See, you'll be surprised that this is coming from this. See, like the Gibbs-Helmholtz, in a sense, Gibbs-Helmholtz. When you write in terms of equilibrium constant, in terms of Gibbs energy, Gibbs-Helmholtz. So this is Van 't Hoff equations. Same, these are actually alternatively. These are so very good, very good. Shall I remove this? All these things, okay, very nice. Okay. So what is the topic now? See, topic effect of temperature on equilibrium constant K. Yes, sir. Yes, sir. So this is there. Huh? So just quickly remove this. I don't write this in case needed. I will come back to this. Let's start. So this now from this corollary. dt minus 1 by t square. Thank you so much. It is wrong. It is wrong. It is wrong. Please check this. dt. I am very sorry. d1 by t is actually that. d1 by. I am sorry. Good. Very good. Thank you. Okay, you just correct me in case I have made a mistake. Okay. So this. Very good. Now note corollary. 1 by 1. For endothermic reactions, that is delta H or delta H0 since is pertinent. Delta H0 is what? Positive. Delta H0 positive. What will happen? Your conclusion is what? See here. You apply this one rather than this. I will tell you, suggest. Positive means negative. That means when that is K. I am writing. Follow me. K negative to K decreases negative as 1 by t increases. Do any difficulty following this? Easy. dy dx you have to consider this. That is 1 by t increases means t decreases. So t decreases, k decreases, or right here, or t increases as t increases, equilibrium constant increases. Conclusion, inference. What does this mean? How does it help us? What's the use of this? Now, why are we writing this? Why are you coming here to take up this course? What's the use? What shall I get out of this? In your life, in your projects, you want to favor a certain reaction. Suppose you want this direction, I want that reaction to occur. Means equilibrium constant. Equilibrium, so where it will stop. You want to extend the conversion, means increase the equilibrium constant. So maybe further to the product side. So you want to increase the equilibrium constant. Clue. If it is endothermic reaction, underscore, then increase the temperature. If you don't know, randomly will do. So decrease, sometimes increase, everything. But this is a science. Okay, and happy. Okay, equilibrium constant. You have a certain reaction. You want this to occur, and for exothermic reactions, right? Exothermic reaction. Quickly. Now it is easy. One delta H0 is what? Tell me, negative. You will enjoy if you participate. So K will see negative, positive. So K increases as 1 by t increases. That is t decreases. Is okay though? Write once more. Or as t, left hand side is convenient to us. As t decreases, K increases. So one case t increases, another case t increases, K increases. In another case, T decreases, K increases. Exothermic reaction, you have to, if it is exothermic reaction, then you should not increase temperature. Since suppose you want actually, suppose you don't want that reaction, you are studying a reaction which you don't want to occur, or if it occurs to a small extent only, then means you want to decrease equilibrium constant. Good. If it is exothermic, increase temperature. So this is so many things. One line I may write 20 lines. Okay, okay, good. So I remove this. Is no. Achha, another point. Another point is over. Okay. Achha, example. If you ask me example, then I'll take up. I'll remove this actually with this quickly. Example: metal plus oxygen, metallurgist, metal oxide, exothermic or endothermic. Exothermic. They were all combination. So make it two. So you cannot see iron, silicon. You cannot run after them. All combination reactions, typical, most. Almost, I have some few examples, actually, stray example, exceptional. Otherwise, metal oxide is exothermic. Delta H 0, tell me, negative, exo. Right? In fact, note, in fact, all combination, most, in fact, most combination reactions, reactions are, tell me, exothermic. Remember this, it helps you. Okay, again, and EG1, right? I'm giving one to distinguish, and then opposite is how, what is good easy example. This opposite, this side is negative, so that side is positive. What is the product minus reactant? Good. If you understand nothing like that, delta H0 is right in so many words. Endothermic. So in fact, right? In fact, most dissociation reaction right here. Dissociation reactions are what? Endothermic. Most dissociation reactions, most right, most. One, I have actually in my life got only a couple of examples. Wow, few only. 1, 2, 3. This that which is actually violate this. So over this part is over. This part. Next is, I want to actually use this place. Now where I will use this, I will write this. Now from this, call it. I write this equation. I am using this equation now for the time. Equations. Conclusion over. Integrating. Call this equation 1. Okay. Integrating equation 1. Equation 1 very important. What is the interest? The moment is differential, sir. Integration is actually further exposed, further convenient, handy. A differential, sir. I want to get equilibrium constant from one temperature and another temperature. From one temperature to another temperature, integrate. You know this standard thing. So you integrate d ln k. Let me write. Shall I? Is right. Delta H0 by RT square. This will be sufficient. Integration, please. I don't need this. dt ln k. Acha. Shall I? Or integration, tell me T1 to T2, as you know. And it is also corresponding k T1 to k T2. Or I'm writing here answer. ln k T2 over k T1. Easy, very easy. Sometimes simple things. Minus delta H0I, I'm very sorry, R 1 by T2 minus, please check. So we will box this since it looks like important. Let us enjoy this. This is just you frame a problem. You Anurag, you frame a problem. Use this. You are giving some students. You want them to apply this. So suggest a problem.
So suppose the equilibrium constant will be given at a particular temperature.
Good.
And another particular temperature will be given at the equilibrium constant.
Then he will be able to solve.
He need to know delta H.
Delta H naught. So that you have to supply. Acha. Moreover, any is a correct answer. So equilibrium constant, one temperature you are dealing, and you have got in the literature data book another temperature. So convert. Don't worry, convert. But one thing I have assumed. Can you tell me, Sukolan, what I have considered that may be actually objectionable, doubtful? Are we entitled to do this? Here, only here. Here to here. No, nothing here. Here to here. Anything it looks as is it fair, sir, to do that?
The composition is fixed.
No, you are answering. You are not answering. Composition is fixed. So what? It's standard state and equilibrium constant for any reaction. Equilibrium constant is not standard state. Standard state gives the equilibrium constant delta G. Composition is not fixed. Now nothing is about. See here. It is your high school or maybe first year high school. Delta H is considered independent of temperatures are taken outside. Sir, heavy. Sir, taken. Is it free, sir? No. Is it? Now the question. Since if this is the problem, do you agree that delta H0 must be a function of temperature, or is there any doubt that delta H0 cannot be? Is not function of temperature. Is function of temperature. Are you sure?
Here we are considering
delta chemical, any chemical reaction, and that delta G0 value. No? Delta G you have to handle that. Delta G0 means that is delta H0, delta H0 all are there. So nothing. Metal plus oxide is metal oxide. So I'm just wasting low, but it is interesting. Enjoy this. Delta H0. What I'm asking that yes, delta H0 is function of temperature. Are you really doubting this? It's not function of temperature. Or if it is function of temperature, why? How? What kind of functionality? Where have you studied it before? Anyone? That is Kirchhoff equation. Delta H of a chemical reaction is a function of temperature. Metallurgist actually is bound with temperature. Anytime temperature, phase diagram temperature, heat treatment temperature, anything, all temperatures. So there you started. Enthalpy change is a function of temperature, chemical reaction. Today, equilibrium constant also standard free energy change function of temperature, entropy, same way. And today, equilibrium constant, final form. Is okay? So it is also a function of temperature. Oh, so it is a function of temperature. But I have considered this.
delta H
Delta H not, or delta H or delta H not. Is
constant for any reaction.
no, it's not function of temperature then. Then what is Kirchhoff equation? It says is a function of temperature. Under delta H T2 Kirchhoff equation. Delta H T2 for the standard anytime. If it is standard, that whole thing standard. Delta H T1 plus delta Cp Tt. It is integrated from Kirchhoff. And what is the differential from? I'm showing you. ddt delta H under constant pressure is delta Cp. Delta Cp. dH dt is Cp. Goes back to the first base class. dH dt is Cp. The d delta H delta Cp. Constant pressure. I can write same composition, and this is actually when standard state. When standard, this will be delta G and delta Cp is actual delta Cp. We don't consider. So this. So if you want to use this, you see standard state. So apply, and this delta Cp0. Then no, it is not over. Then when I am entitled to this, I have done this simplification. Well, this I said first semester, first class test syllabus, not even saying the second class test. When delta this is sensitive delta Cp. If it is 0 or negligible, very small, out, then send, then independent. When it is 0, independent, delta H is independent, means it is as good as a constant outside. But when delta Cp is 0, delta Cp actually is a very serious issue. My point, okay. So every time you follow, what is actually again here how you see equilibrium constant is a function of temperature. But functionality depends on what? Function. Who on which this functionality is sensitive? Which governs that functionality? That dependence. Which governs? Yes, it is governed. It is function. But which governs? Which you look at to which parameter actually quantifies that dependence. Look at the voltage. If negative, positive, if negative, hot value negative, more negative, less negative, positive. So this is always true. Equation. This is about the equation. Any equation. Okay, not for this equation. So you are right, though. So what tacitly consider that simple thing is delta CP is 0 or actually exactly 0 but close to 0. If it is not, then what will happen? Then you cannot take this. That I'll discuss today, time permitting. Okay. So that is actually our second topic. This is the first topic that I am discussing. So shall I write here? I can take this one. Can I remove this? This is not. It's over. This part is over. This part is all over. So I am writing you for you when, just in case you want to be very punctilious. Okay. So when delta is 0, tell me, is not function of temperature. This whole life, okay, lesson, whole life thermodynamic lesson. You follow the, no, if you follow first class, you have no difficulty in the second class. This is one lesson. If you have done well in the first semester, you don't have difficulty in the second semester. Like this, when delta is 0 is not that is when Omarto, then that is when what's the name? If it is a function, then it come outside the integration. And then this is true when delta CP 0 or that's very clear. Exactly, it's difficult. These are experimental data, very difficult, but close to negligible. So it's okay though. Over. This segment is over. Very nice. Very now effect of pressure I will take up. I remove this. This part is over. Thank you so much. Thank. How much? 40.
46 minutes.
Okay, that's not bad progress, but I have covered satisfactorily. It's okay. Start. Effect of pressure. Effect of pressure. Next slide. Next. Effect of pressure on P means that is pressure. Effect pressure. It's right here. Top. This temperature. Shall I write here? Temperature. This is pressure. P is pressure. So effect of pressure P on equilibrium. I am writing equilibrium actual conversion, right? Equilibrium conversion. Sorry, okay. Okay, on equilibrium conversion. Right. Conversion given by kx. I'm writing this. It's unnecessary talk. On equilibrium actually. So start. For this, consider this a little bit. A little bit of discussion or also mathematical derivation. So consider the reaction. Follow this. Follow with me quickly. Consider the reaction. A homogeneous reaction. Gas phase. Consider the gas phase reaction. Gas phase is homogeneous. Homogeneous. Gas phase is homogeneous. I don't write. You know this. All this unnecessary. Reaction is what? B. Let me write. B gas plus C gas goes to D. Is correct. I have correct. D gas. It's very good. I'm writing this. Equilibrium constant is what? Start. This case, remember I'm writing here. Since for some reason I have to again remind you or underline this. Thermodynamic equilibrium constant, which is unique. No one equilibrium constant, and it has its delta G0 is minus as it is obtained from delta G0, and you all know this. Remember, and we'll consider this K is what I start with. This I start very easy, simple reaction K. You have number. So what's the right activity? So write quickly, just for your benefit, quickly activity of D, activity of B. power actually. Activity of C, power C, right? Since gases, gas phase, remember, note it is equilibrium. Huh? I'm writing once, but I will not write later all the times. Tag this. This always. Beginners always do equilibrium. Sorry, constant equilibrium. Equilibrium activities. What is this? Partial right? What simplification right? Let us see how much you retain. What simplification? Activity, partial pressure. Easy. Most of the things you will see later easy. Because it has been made easy, that's why it is so much time consuming. And if it are not time consuming, it is fast, then nothing will be easy. Nothing will be actually understood. This is the whole thing. You see, you check this, verify this. Yeah, I can write many. I could write. Why you don't have to explain from this? You get, and you will not. Next day you will not come here. Next day I cannot see you here because unnecessary visit. Nothing there are writing something, but explaining. Okay, what is this? Partial pressure. Remember, explain. Yes, Sukolan, explain why partial pressure. Ratio, and the denominator is 1 and square. Understand? So please, don't ever forget this partial pressure quickly, quickly, quickly. Huh? So is partial pressure is mole fraction time total pressure. Recall this. Because you cannot forget this. You can afford to. Mole fraction time total. I'm writing this. So I'm not writing all these things. This means I'm writing main things. Again, I'm writing here equilibrium. What is the pressure P? I will note here. Except P, tell me. Excite times total. বোর্ড শিফটিং না একটু ঠিক করতে বাবা একটু শিফট হয়ে গেল না একটু আচ্ছা এবার ঠিক আছে সো পি ইউ রাইট ডি মাইনাস বি প্লাস সি নো ডাউট noting recall pi is mole fraction times total pressure. I'm not writing anything. Pressure is total pressure. P is the total pressure. Total pressure, and pi is the partial pressure. Good boy. So what is this? A new thing today. This is your kx. This is your kx. New equilibrium constant, modified equilibrium constant. This one times p to the power delta n. Or delta n is where delta. This is right 1 by 1. Kx is the modified, not true. This is the true equilibrium constant. This is the thermodynamic equilibrium. Underline thermodynamic. You have to write this is a modified. So I remove all these things. Don't make clumsy. Modified equilibrium constant. Modified. I mean distorted. Not true. Fake. I'm sorry, not fake. Fake is too much of it strong. It's actually apparent. Okay. No, not thermodynamic equilibrium constant. Not K, sir. Clearly see K and Kx are different, separated by this factor. Modified equilibrium, all the same equilibrium. They refer to equilibrium. Equilibrium constant. Modified equilibrium constant. Kx. Happy to? Kx into p to the delta n. Or right, or equilibrium constant written in terms of mole fraction, written in terms of mole fractions. That also you can use. But this is modified and not true. Okay. So right, so we get what is delta n? Delta n is moles of product minus moles of D is the product, right? Moles of product quickly. Products minus moles of reactant. Quickly. Easy, so easy. You know perhaps some of them. Quickly. Okay, very good. So I'm writing once more. So that is plus K is Kx p to the power delta. Okay. Now see, we want to study the effect of pressure right here. To study what we are aimed to study the effect of the pressure. To study the effect of pressure. Now, what you see? At a given means when you study the effect of temperature means what happens at a implied is what? Implied what? Tell me at a given temperature, because temperature that is everyone knows. So at a given temperature now K is Kx. How I will ask you, you will not be able to answer perhaps, or maybe you will be able. At a given given temperature, and as pressure changes, what happens to K? At a given temperature, as effect of pressure means pressure changes. What will happen to K? Will it change? K never changes with pressure. This is very interesting. Very important. K is solely a function of temperature. Like note, K is solely a function of temperature. So remain constant. Solely a function of K being solely a function of temperature. So that is why this is so. Because follow this. Delta G0 is, tell me, minus RT ln K. Follow this. Proof, quick proof. Whole life proof. Equilibrium constant never changes with pressure. Only it knows only temperature. Okay. Delta G0 is minus RT ln K. Delta G0 is what? Tell me. Delta G is a function of temperature. Delta G0 is a function of temperature. Do you know this? What is this? I tell you which form? Which form? I tell you. A plus BT form. You have got this now? You have got this there. Okay, what you have got? So many data. Delta G0 na? This minus this. So A plus BT form. So T is there. So these are constant. You may write constant. B is a constant. And temperature is a temperature. So what you are getting from this? Tell me. ln K is what? Tell me. See, I'm going to establish this. A plus BT by RT. Nakire, minus RT. Or what it is? Minus A by RT. Simple minded. Minus B by RT naki. What does it mean? What does it mean? K is a ln K, or K is a function of, but this constant. Hence, so K is function of temperature. Follows from delta G0. Acha, by the way. Delta G function, solely function. Why delta G function of temperature? I wrote this. A plus BT, very good. But the standard state finish. Why is it solely a function of temperature? Standard state. Go to the definition of standard state. What it says? At the temperature of interest. So means there is the clue that as temperature changes, it changes. Pressure, immovable. One atmosphere. And purity, pure. If not 80%, 90%, then it will be actually flexible, but pure. So good boy. So K is a solely function from the definition of standard state. From the I'm writing this much only from the definition of standard state. That's okay, though. I got it. So you see, so I'm writing. So I write here. K is a constant. For a given temperature. For a given temperature, I'm writing for a given T, K is Kx P to the power delta N. So this is a constant at a given temperature. So if you now apply this, tell me corollary, like this previously, corollary. One, when delta N is positive, follow this. When delta N is positive, for a reaction, when delta N is positive, what you get? Right, you write yourself. As P increases, right here, as P increases, Kx decreases. P increase, follow this. This is a, take your time. Is okay? This is okay? Like the corollary of Van-Tropic equation. One is endothermic, another is exothermic. One is endothermic, another exothermic, Van-Trop. Two corollaries. Here two. Delta N is positive, means product moles are greater. So as P increases, what will happen? What is the impact? kx will decrease because this cannot change. No one can move you. The moment you actually know, be persuaded by them, the case will change also, not to some extent. Then gone, all gone. K steady with when temperature steady. Kx decreases. Kx because Kx is signifying the what I wrote for here equilibrium conversion. That is right here. That is right many things here. Two things. That is equilibrium conversion decreases. That is yield. What is yield? Yield, how much I am getting actual product. Okay, forgive me. Yield percentage. Yield percentage decreases. Please write this. It helps you. I am giving an example. Before this one delta and second is in when quickly when delta n is negative again as p increases, tell me what will happen. Kx negative, opposite negative means as p increases means whole thing is decreases, so kx must increase. So you write here yourself, conversion increases, equilibrium conversion increases. Example, please follow. This example are easy. One example, easy example for you. What is this? Ammonia. Ammonia is what? Ammonia dissociation. 2NH3, although very simple, non-metallurgical. Metallurgists also use this. Will you? Is delta N positive? Okay. But this is more important to you because this includes ammonia synthesis, Haber's process. Haber got Nobel Prize in chemistry. So what is this example? Opposite. N2 plus 3H2. Shall I write gas plus 3H2 gas goes to 2NH3 gas. So what here apply? I'm detailing here because this is Haber process. Ammonia synthesis, right? Ammonia quickly synthesis. Good boy. So what is this? Ammonia synthesis. So you tell me here delta n is what? Delta n is, tell me, delta n is second case. Delta n is how much? 2 minus 1 plus 3 is minus 2. So as p increases, so what you recommend in this case to increase the for given amount of input nitrogen and hydrogen. If you want to get more ammonia, obviously you will get more conversion into ammonia. Then what you will do? Increase P, and that is actually done in Haber process, higher pressure. So as P increases, Kx increases, or you can write yield percentage of ammonia increases. Yield reported in percentage. Yield percentage of ammonia increases. Is increases. Over. So this part is vital. Next, I'll take another example right here. Another example up top. Very important metallurgical. Another example. Right here. Start this. I'm taking here another example. So remove all these things. Okay, it's all done. This will be very important to you. In fact, very important. Perhaps you are coming from the examination yesterday. Last examination yesterday, I guess. You'll see. Readily follow what I'm saying. Another example. So start here. Another example, another metallurgical. Follow this. Another example, metallurgical. What is the reaction? That is very important to us. CO2, right? An example, which is also heterogeneous reaction, right? Which is also what I consider this homogeneous. But you see, still it is maintaining. Very interesting. It is still a K is Kx. I box this. Box here. I will actually maybe I will remove this side perhaps. A box here. I will turn here. Heterogeneous, which is heterogeneous reaction, which is a heterogeneous reaction. Heterogeneous reaction. So what is that? CO2 gas, boudoir so-called, goes to 2CO gas. This is so-called known as the carbon gasification reaction. Good, very good, right? That carbon in blast furnace, carbon gasification, solution loss, carbon gasification reaction, boudoir reaction. Okay, in blast furnace 2 years. Reference blast furnace. I'm sorry, blast furnace stacked. Blast furnace stacked. Okay. Okay. Stack or what? Okay. In blast furnace. This is blast furnace actually means stack.
Not in stacks,
Stack. Okay, stack as by in blast furnace. Stack or what is this called? Next is boss, and then heart. And the 2 year actually, no, 2 year carbon oxygen gives you CO only. There is no this equilibrium, but this is CO2 percent is very small, they're negligible. Blast furnace. And then actually as it goes up, as goes upward, actually it is range. Okay, don't worry. Okay, so reference blast furnace. Okay, stack or okay, blast furnace. Let's have blast furnace. Stack actually. Don't worry. What is this? I'm writing. Follow with me. K. You enjoy this. K is what? What's all right? K means when I write K is thermodynamic equilibrium constant. K is what? Again, quickly. Activity CO square. So if you cannot do anything, I'll just do it. P CO2 activity. Sorry. CO2 active. I mean, in case you actually have any difficulty, you don't actually feel well, it's calm. So I'm writing activity. So I'm okay. I have not skipped anything. Okay. So equilibrium, as you write, always equilibrium. Then quickly tell me what shall I write? This is PCO square PCO2 activity of carbon. And remember, it is a carbon saturated system. Blast furnace is a carbon packed with carbon. So activity of carbon is one, right? Carbon saturated system, that is given, that you are at liberty to consider. For carbon saturated system is activity of carbon is 1. Okay, good boy. Achha, now keep on you want to reach here. Baba, Paul? I'm coming to this. This Pito. I'm coming to this. Partial pressure. Yeah, also here, if you forget this, partial pressure, then mole fraction time total pressure. Remember this. What is partial pressure? Tell me. XCO square by XCO2. PI is right here. PI is in case you are actually digressed. Okay. PI is X into total pressure. So into right here. P square by T, actually this is actually this. So what it is? Right here nicely. XCO square by XCO2 P. Make it. What is this? What right here equilibrium? By means just at the end again tag equilibrium. Tag may not be in the intermediate state. Equilibrium. What is this? Kx. This is your Kx for this reaction. Why you follow me? Kx times P. Achha, why Kx, sir? Equilibrium constant in terms of mole fraction. What is the equilibrium constant in terms of thermodynamics? Is what here? What is you written here? Activity of carbon gun. So this is the effective formula. Gun activity, truly activity, and it is only in terms of mole fraction. Remove A as X. A by X. So it is certainly the Kx. Okay, and P to the P. Here note. Achha, let us say I'll explain one thing. I ask. Note delta. Yes, delta n. Note delta n is what? Yeah.
Number of moles.
Here. Follow.
Number of moles is the product number of moles.
Let us see. Tell me. Product side have 2.
2.
And left hand side.
2. 1.
Why 1?
Carbon is solid. So we are not.
No. Why not?
Activity is 1.
Otherwise, it's a Kx. This comes from ideal gas equation. All. Partial pressure is PV is NRT actually. All. So this is applicable for gases only. So only gas right here. Most of gas molecules are pertinent. Solid cannot. Partial pressure on solid, nothing. Okay, so you see these are actually P is Kx, partial pressure is partial mole fraction coming from where? PB is NRT, PI is, see my point though? Total, actually how it is getting, PB is NRT. In basic source is ideal gas equation, gas. So delta N is right here. I am writing for you number of gas molecules. Never ever. This is major mistake many students in semester class test. Number of gas molecules, gas moles. Number of reactant gas moles minus number of product underlying gas number of product gas moles.
It will be product minus reactant.
Thank you so much. You write 100% product gas moles and right here reactant. Thank you so much. How many now tag with this? What is this? Product is 2 minus 1 is 1. So note delta N. So this takes the form. So this gives the this is in agreement with the previous form. This is also this is in agreement with the previous form. What is the previous form? Write yourself. K is Kx p to the power delta N. Box this, previous form. So you all happy. Okay. Achha, sir, can I remove all these things? Remove all these things. Now one by one you follow with me. Follow. Effect of temperature you have started? Quickly follow. Pressure, effect of pressure. So I'm actually giving you, I'm sketching you actually this one, effect of pressure. So this I'm giving you a sketch here. You follow this. Percentage CO, this is your plot in CO2 mixture. Follow CO2 percentage CO on the y-axis. This is giving you this. This is your famous. This is your curve. If you draw yourself, you'll get this curve. You get this curve. This calls okay. This is right. CO2 C saturated, right? Saturated. Carbon monoxide equilibrium curve. Equilibrium curve. This is right here 100%. This is 0%. You know what temperature it is? Close to 1000 degrees centigrade. And this is about close to 400 degrees centigrade. So between 400 and 1000 is that moves. And when it is 50%, you know, 50% is I'm giving you, give mark here 50%. Is actually 675 degrees centigrade. Remember, these are interesting. 50%, 50%. CO in CO2 mixture. I'll show you. Right? What is the x-axis? Right? Temperature. And what is this temperature? Right? 5. It is actually important. 675 degree. What is this in Kelvin? 48, 948 K. Okay, so no problem. So I'm sketching you this. What is the effect of pressure and what is the effect of temperature? So study the effect of temperature and pressure on equilibrium. Okay, equilibrium composition. Equilibrium on equilibrium, considering the current example. Consider the current example means current example. What is CO2 plus quickly? You enjoy this. CO2 plus C is 2CO quickly. Follow this. Let me write. I'm writing you. I'm writing one systematically. CO2 gas plus carbon solid 2CO gas. Some pertinent information is required for you. I'm giving you, which is important. Delta H0 is a what type of reaction? This is endothermic. This is an endothermic reaction. Okay. Delta H0 positive. So right here in bracket endothermic. So first you clear the effect of temperature, which you have already done. Done means you have studied. What is that? Van Top equation. Van Top equation. Achha, you ask me in this context. I will tell you. So, okay, at the end, endothermic reaction. Endothermic. So as T increases, what will happen? K increases. K increases. Okay. So if K, as T increases, K increases. Okay. Achha, this is for another point. What is missing here? By any chance, can you answer? What pressure? Correct, you are correct. What pressure? At 1 atmosphere. This is drawn for 1 atmosphere. When it is said 1 atmosphere, means this is a function of pressure. If it is higher pressure, it will be a lower curve. So this is right. 1 atmosphere means total. 1 atmosphere total pressure. This is certainly correct. Okay, this is the effect of pressure. So as T increases, equilibrium constant increases. Okay. So what you are getting here from this here? Tell me. From this, K increases. So K is what? K is K increases. Tell me what is this? Tell me. K increases. So K as T increases, K increases. For a given pressure, say 1 atmosphere, for which I have drawn. So what will happen to this? What you again write in case you have difficulty? K is Kx times P. Okay, P is constant. So as T increases, K will endothermic. Well, Mantle increases. Remember, endothermic reactions are favored at high temperature. Please write. I have forgotten to write. Endothermic reactions are favored at high temperature. Exothermic reactions are favored at low temperature. Okay, this is thermodynamics. Okay, as T increases, what will happen? Will K change? As T increases, K change. K of course change. If anything can change, that is temperature. Equilibrium constant. Thermodynamic equilibrium constant. The function of temperature, solely function of temperature. Pressure it will not. Okay, because that is by definition. You cannot avoid this. So K increases. So what is common? So pressure is at a given pressure. At a given pressure means P constant. So what happens? Kx increases. Follow straight. What is Kx? That is, tell me, x CO square by x CO2 increases. What does it mean? Mole fraction means mole percent CO. That is, that this gives you, that is percentage CO increases. Take a look. Can we show this? Is it graph? How we show this? Like any reference point? Say this point. This point too. Okay, yes, they won't try. Show this. Percent CO has increased. As you increase the temperature. This is against temperature. Obviously, temperature is changing. So from this point to this point, by increasing. Makes sense? So this is actually, see my point, and converse. Okay, Aditya. The effect of temperature is clear. So it is clear. It is. So okay, I can tell you. Acha, I can tell you. Right. This is maybe say 675 degrees centigrade. 775 degrees centigrade. Maybe. Just example. So it is increasing. I say so here. Happy. Over. Effect temperature is over with this heterogeneous. Effect of pressure. Next. Achha, how will you get this? I tell you what happens. Can I remove this one? Okay, I think I can remove this. Achha, I'm showing you this. See, experiment. You experiment. You take how will you experiment this? How will you draw this curve? You take C gas, carbon dioxide gas. Initial state means non-equilibrium.
This is solid.
I'm sorry. Thank you. Carbon solid. I'm very sorry. Initial state. State 1. Initial state goes to non-equilibrium. Right? Initial means non-equilibrium. What temperature consider? Say 675. Say 675. Then what will happen? What is the corresponding equilibrium state? Tell me. You will understand from this, okay?
CO, CO2 and C.
Okay, wait a bit. This is under constant pressure. So make it sensible. P is 1 atmosphere. Then what will happen? What is equilibrium state? Can you draw this equilibrium state? Draw equilibrium state. P is 1 atmosphere holds there. Held there because you 1 atmosphere curve. What is the equilibrium state? Tell me this 675 right here, 675 degree centigrade. What you will get here? Tell me carbon solid means it is excess intact. What are the gas? CO2 react with carbon, making CO and it is CO2 mixture. You always see the whole domain is CO2 mixture. Fully CO about 1100 degree above that to not 100%. Never. That's never. And 400 degree centigrade below essentially CO2. Again say 0.100% again 99%. So what is this gas? This is right. What state? Equilibrium state. So final state. Final as you state 1, state 2. State 1, state 2, right? Equilibrium state. Equilibrium state. What is this percentage CO2? This mixture? What is the answer? Sir, 50-50. Here because this temperature so chosen that it is 50-50. This is. If it is 60, then it will be maybe higher temperature. 70 still higher. Okay, so right here. Percentage CO is 50. Percentage CO2 is 50. Okay. Now how you show this? The moment you actually have this equilibrium though, give the temperature 675 degree centigrade. Right here 948 Kelvin. Also attach Kelvin because it is. Now how you demonstrate this? This experiment. Equilibrium. You increase the temperature. Thermostat and the thermostat or furnace controller change the setting to what? If 650, so I'm writing since I'm saving place as if 775 degree centigrade, then what it will be? It will this equilibrium is actually not okay. What is this called? Compatible. 775 degree centigrade and 50-50 is not compatible. 670 is very good, sir. That is equilibrium. It is non-equilibrium now. It is not equilibrium. It is searching the corresponding equilibrium. And so what will happen? What will happen inside? Tell me. You tell me what will happen inside. The moment it makes 775, what will happen? More of reactions. More CO will be formed, means more CO2 will react with carbon. CO2 will further react with carbon, forming more CO. And so, can I write this? So, there you have got an idea of this. P is 1 atmosphere. Don't change this. Write CO2 CO like before. Carbon solid before. Again 7. What is this called? 775 degree centigrade. Right. Final equilibrium state. Right. 775 equilibrium state. Right. Equilibrium state for what? Somehow I actually reached the bottom of this. 775 degree centigrade. What is the what has happened? Changed to percentage CO as we have considered. Maybe I write here 15. I have given any value previously. Any value? It is 50-50. So give certain value here. 60 maybe. 60, 775 to 1100. 60 then 60. So what it is? Percentage CO is 60. Percentage CO2 is 40. This is the demonstration. Okay, equilibrium. You attempted equilibrium, you reached equilibrium. All these things. Okay, very good, very good. Constant pressure you maintain this. Okay. Now effective pressure. Next is effective. Shall I remove this? Yeah, effective pressure. I remove this part. And this diagram I don't want to. Effective pressure quickly. This is also interesting. You know the answer. You have already got the answer now. What answer you got? As for giving pressure, effective pressure is what? Have you not? It's effective pressure. Acha, right. Effective. Let me write. I'll clarify you. Yes. Let us discuss. Discussion first, then graph. Experiment, graph. Also. Effective pressure. What is the relation? What is the relation you have? Tell me. Means what is the implied? What is the implied thing? Effective pressure. What is the implied? The temperature has not changed. This time temperature is not changed. So same temperature means like vertically, something will vertically upward or downward. whatever will happen. So suppose this temperature is your chosen temperature. This maybe I'll redraw this. Okay. So from this actually, effect of pressure. First of finish this. K is Kx P to the power delta n, starting point. Right in bracket at a given temperature. Given temperature. Okay. So okay, given temperature. Good boy. At a given temperature. So K is, so what shall we write? Yes, Devbom, what is your idea about K? This is my topic. Effect of pressure at a given temperature. What you write immediately from K? Constant. Constant. That helps you. Constant. So P delta n is what? What is the delta n here? Tell me delta n. Already have you? One. CO2 on to. Reaction is here. CO2. One. Oh, good boy. You one. One. P to the power one. As if. So Kx times P. So as P increases, I'm increasing. As P, that will be better. As P increases, Kx, sure. That is, what is Kx? Tell me clearly. Kx, xco square by xco2 decreases. That means obviously CO decreases. That is, that you can very easily. Actually, xco plus xco2 is how much? Xco plus xco2 is how much? 1. So you can very easily find out what is individual values, okay? Because you have another equation always. So that is percentage CO. Tell me, percentage XCO, right? First, right? That is XCO decreases. That is percentage CO. I'm writing so many words, so many lines, so that they have no, okay, lapse, okay, no difficulty, okay. Percentage CO decreases. So I'm drawing this. So which one are you drawing? See, so I'm drawing this. So I'll see. So one thing. How these graphs are drawn? How these graphs are drawn, sir? Who drew this graph? Author, how did he? Did he carry out experiment? No, you did it today. You did, yeah. You take this, you CO2 CO, you take gas analysis you do. Take this gas. See, you see it is 50-50. Gas analysis, how to do infrared analysis or gas chromatograph, you can get what is the percentage of CO2. So you can get this and you'll get this point. Similarly, change the temperature, another point, and you can draw the graph. And also you see, you can draw actually what is, how you can draw if you don't, another way to draw this graph quickly. Achha, tell me how to get this, just in passing. How will you draw this graph? Suppose you don't have this graph. You want to draw yourself for some reason. It is a different task. Nothing to do here with this. So how to draw this? What you will do? I tell you. I follow with me. Equilibrium constant is, I have written somewhere. You know the equilibrium constant. Don't you know? Equilibrium constant?
Yes.
Delta G0. Equilibrium constant, delta G0. Delta 0 is easy, host of data, all possible data on Earth, delta G0. So K is known. What temperature? Suppose one data, if I teach you, you learn, you can find all other data, and then you could draw the graph, connecting them. This data. So no experiment, because you are using others' experiment. What is that experiment? What data? What experiment you are using? Others? Which experiment? Delta G0. That is experimental data. Someone did, and you'll be glad to hear when I was taking lab there, fourth year, second semester, they used to find delta G0 for this experimentally. Or calcium carbonate goes to calcium oxide plus carbonate. So don't worry. This is a different story. So delta G0. So K known. Come down here. Yeah. P, you know what your system is open to atmosphere, or also 1 atmosphere you have maintained. Okay, 1 atmosphere. If it is this, then give me 1 atmosphere. You are theoretically drawing. So P1. So what is this value? XCO square by XCO2 is known, and XCO plus XCO2 is 1. Each XCO is known. Means percentage CO is known. XCO means percentage CO. So 1 point I know. I know other points. That's only I will change the temperature. Means who change the temperature? Who will change? If I change the temperature, who? Yeah. In this 100%. 100 more than delta G0 is a function of temperature. Delta G0 changes, so has changed the K. So changes again new percentage ratio. Another one. Another one, you draw this curve. And then with computer, my students used to do this. With computer, actually, they used to draw this curve. Okay, Boolean curve. Okay, what is it? By solver program, software. So many ways, but you can do yourself. So this you get satisfaction that I can draw myself. When you use in the sentence I, then I is in two ways. One is actually negative way, or say what say, or is actually I should say unpleasant way. When you boast, yeah, I have done this. Another is I confidence that I have done myself. Okay, like this. Okay, that is very silent actual utterance. Okay, so very good indeed. So, quickly, where I am here, what discussing here, what is this thing? I actually lost the clue. Effect of what I am going to discuss now. Effect of oh yeah, right. You know, percentage of decreases. So you understood. That means what I shall do effect of pressure to. That means say follow. This temperature, which pressure? 1 atmosphere. Now 10 atmosphere say. 10 atmosphere. So I'll get the point either here or maybe coincide. I do not know. I know that actually what will happen, it will be below. Because you have already seen this. Percentage decreases. So that means this will be somewhere here. Below. Now this point means all other points similarly. All other points you will get. So another curve, instead of 1, it is 10. Moreover, you are not carrying out experiment. You are just substituting the value. This is 1, another case, this is 10. Happy? Temperature unchanged. Temperature. So for this, it will be down here. For this, down here. So let us not. I'm very sure actually. Anyway. Actually, 10 hours square. Yeah. You follow this. So this will be where here. Oh, sorry. Where I mean, yeah. This is hot pressure. Tell me, 10 atmosphere. This is once more here. 1 atmosphere is written. Shall I write once more? It is written here already. 1 atmosphere. Otherwise, same. Otherwise, CO2, carbon saturated, CO. That means experiment wise, you consider 10 atmosphere. Then experimentally you get this, and when you are using others data, delta G0, you do yourself calculation. So get this point. Now what I am trying to see, I don't have to. Okay, I have already expressed. So 10 atmosphere, what will have percentage of decreases. So what is the corresponding point? So 2 points I showed previously. Follow. Color chalk will help you. Does it help at all? Acha, this was previously effect of temperature. Now what I am doing? Effect here to dotted দিচ্ছে pressure. Follow effect of temperature. Temperature changes, pressure constant. 1. Effect of pressure. Temperature unchanged of 675 degrees. Pressure, it falls. This is the effect of this. Okay. So this also I have seen. Okay. I tell you what. Even if you hear what will happen, I tell you. Suppose you have get 50 though. Suppose you don't have to carry out from here, anywhere. Knock off this pressure. Reversible process, irreversible process. Make it 10. Make it 10. If it is a horizontal furnace, flow reactor, make increase pressure, high pressure system by some building up some resistance, high pressure system. Okay, like vacuum is low pressure system, high pressure system. Then high pressure, you make this. Then what will happen? Now tell me. Okay, Sukolan since actually I have 10 atmosphere. So it is equivalent to for the hot temperature 675 degrees. First one, equilibrium. We are happy, satisfied. Now I upset P is 1 atmosphere to 10 atmosphere. Like previously I upset how? 675 to 775. Now P atmosphere 1 atmosphere to 10 atmosphere. What will happen inside?
Sir, there will be the percentage of CO will decrease. There will be backward reaction.
Good boy. Inside reaction will move in the reverse direction. Twice C goes to CO2 plus. So the carbon monoxide will fall, carbon dioxide will build up, rise. And this is the whole story. So effect of pressure, temperature is over. I think that this is this much I wanted. Another this in this connection, one principle which is high school students studied, but I'll give you a little bit into that. Le-Chatelier principle. These are actually Le-Chatelier has summarized this in a qualitative way, not quantitative. So quantitative, you are already so smart that you don't need any other principle, but still sake of, for the purpose of completion. So shall I remove this? I'm writing this. I'll remove all this thing in case it is needed. Quickly, this is the end of this topic. These are large, okay, longer topic. Then the next one. So what is this? Quickly, Le-Chatelier. Last in this context, this is my last actually subtopic for this broad topic. Le-Chatelier consider Le-Chatelier's principle. What it says, you have already understood. If if temperature, right, in language, if temperature or pressure or composition of an equilibrated system तो system they say of an equilibrated, already equilibrated, of an equilibrated system changes is changed the system adjusts itself to nullify the effect of the change. This is the message, right? I'm writing here, explaining here. That is, the system moves from this is not stated, but you will follow it. The system moves from one equilibrium state, which it was initially before the change, move from one equilibrium state to another another one. This you should note, equilibrium to equilibrium, that will be changed. So what it says, nullify, you need to follow. Note, Le-Chatelier principle is a Le-Chatelier's principle is a qualitative statement. Is a moves. How long it moves? Where it moves to? We don't know. No comment. The principle is a qualitative, right? Qualitative statement. While Van 't Hoff equation or what is that equation? Effect of pressure or K is Kx times P to delta n to. That's the effect of pressure to. Or the equation, right, this is better English, or the equation K is Kx P to the effect of pressure actually. Effect of Van 't Hoff is effect of temperature, effect of pressure are what? What will say? Are quantitative. Are quantitative statements or equations. Math are there, quality, but still you follow easily. What it says, let us quickly explain. Let us explain this. Let's explain this. You answer quickly. Very good. Very good. Quickly explain this. Ajay, with this, you easily understand. 2CO. This is what type of reaction? Delta H0 is positive, means endo, right? Endo. Like what it says, Le-Chatelier, effect of temperature. What it says? What it says? No, nullify that. You have changed the temperature from one equilibrium to another equilibrium. Change the temperature. It says system adjust, means you search a new equilibrium. That is the meaning of this. So the nullify of that means nullify means it will actually take into account that and adjust itself. So search a new one. That is which you have already found. but his statement you follow. He says, since it is endothermic reaction, endo means it likes it. It likes it. It will actually uh, it requires it for for progress, for further progress of the reaction. So if nullify the, so you see endothermic, if we give temperature, it will move in the directions endo. It likes heat, likes temperature, so it move in the forward direction, moves in the forward direction, and you have seen already it moves in the forward direction in the described here to and effect of pressure, a temperature. I'm not writing this. Pressure is what? What you have got at if you increase the pressure, reverse direction. What it says? What is it? Here, how do you explain Le-Chatelier effect of pressure? It's a system adjusts itself to nullify the effect. What is it? Pressure means, pressure increase means what? Pressure is actually crude. Le-Chatelier is a crude thing. Actually, who one likes actually when this is a quantitative expression, who like this theoretical, who cares? But sometimes crude are good, weak, weak. You will say, oh, moles. You have already understood by before Le-Chatelier that moles are less favored. You have follow. So what is this? Pressure is increase. Pressure increase means volume decrease. Volume decrease means moles decrease. So as pressure increases, it is moved towards the fewer moles, in the direction of the fewer moles. Okay, so which is the direction of fewer moles? This is 1 mole, 2 mole in this direction. This means CO drops, and of course CO drops. And still another is leaving. He left out, that I'm clear, that I'll take up. Temperature, pressure, okay. So fewer moles, pressure increases, I'm writing you for you. In the direction of equilibrium moves, shifts. Equilibrium to equilibrium. Remember, this is a key word. Equilibrium to equilibrium. It means it moves and so what? Equilibrium shifts to pressure increases means volume decreases to the side, to the reaction side having fewer moles, right? Fewer gas moles, gas. Fewer gas moles. It is the Le-Chatelier interpretation or quick inference. Quick temperature. What you will say? As temperature increases, hunger. Endothermic reaction, hunger. Endo. Delta positive. It doesn't reject. It absorbs. So high temperature, very good, very good. Oh, high temperature, very good. Means welcome. So temperature increases. So endothermic direction is favored. Look at it. Equilibrium shifts, right? The same language. Equilibrium shifts in the direction of endothermic direction. In the endothermic direction, equilibrium shifts in the toward the ball toward the endothermic, in the endothermic direction. Shifts towards the endothermic direction. I remove this endo, right here, endo to the end toward the endothermic direction. What is endothermic direction here? CO. This is endothermic to the endothermic. The direction in which heat is absorbed. The direction, so many things you can write. Endothermic, smart endothermic direction. You are all direction. I don't know. And the last one is the concluding one. What I said.
Conclusion.
This is very important for you. This is very very complete this. Okay. Complete this. Effect of composition. Temperature, pressure, composition. You try to follow this. I'm giving you a sketch. Metallurgical system. You appreciate. I'm very sorry. This is constant volume reactor. Temperature is constant. Say 1000 degree Kelvin. Say means isothermal. Right here another one here. Right here, constant volume reactor. Constant volume, constant temperature. Constant V reactor. Now what you have taken? Metal. I'm writing oxygen gas. I should have drawn a little bigger. Shall I? You mind? Can you? So that I can write them. Right. Little bit. Oxygen gas. What pressure? 1 atmosphere in starting. Constant volume. And volume 1 atmosphere. This room 1 atmosphere air, but it is oxygen. And what? Metal solid. Reaction under study. Reaction under study. Metal solid plus oxygen gas goes to metal oxide solid. So what is the initial non-equilibrium? Initial state. Right. Let us compute nicely. Initial state. What is non-equilibrium state? Good boy. Goes to what? It goes to equilibrium. Obviously, all reactions moving to equilibrium. What will happen here? M solid and product will be formed. Reaction MO2 solid. Write that MO2 solid. Again, you write here. Constant V. Oh, constant V. T is and T is sorry. T is 1000 K. So that actually this is right here. What is this? Final state. Final state, which is equilibrium state. What is the oxygen pressure? PO2, right? Oxygen gas, but this has been consumed. This has been consumed and you will attain equilibrium. And now typically this oxygen pressure is very small. 10 to the minus 10, no problem. 10 to the power minus 18 for aluminum system, no problem. This is oxygen potential. Later on. So I'm giving you a pressure. PO2 has been reduced to what value? 10 to the power minus 10 atmosphere to begin with. So far, no effect of composition. Nothing has happened yet. The equilibrium, this first equilibrium. Now disturb this equilibrium. If you disturb this equilibrium, then magic. Add SiO2 to this equilibrium state and add silica solid. Solid or liquid, it can be liquid also. Liquid is easier, but solid also solution. Okay. It would disturb actually. If you change means disturb the equilibrium. I mean adding. So what will happen to this? Tell me. Silica is oxide, metal oxide is oxide, slag. These are slag actually. This is a solution. Slag is a solution. So this will enter into solution and activity of MO2 will remain 1 anymore. Solution means activity always remain. Activity is mole fraction. I told you once. Activity of metal oxide is what? Now in presence of silica it has the same solution, means two things together. Two mole fractions together is 1. Solution means what? Activity is 1 for whom? Pure. It is not okay. So right, add silicon solid and it forms MO2 SiO2 solution. SiO2 solution. No, solid solution. Actually, don't have solution. So as a result, actually right here, it will help you. Write the equilibrium constant. Okay, right here. Okay, shall I write M plus MO2? I'm writing here. M solid. Oh, actually, I should have written there. Planning is here. K. Activity of MO2. First case. Activity of M PO2. Okay. What is this value? Okay. This. Now tell me, when you add silica, what happens to activity of MO2? And it reduces activity of MO2 from change in composition. Means activity is actual mole fraction. Raoult's law says activity is mole fraction. And non-Raoult's law is non-ideal solution says gamma. So activity from 1 to less than 1. Less than 1. Any value less than 1. It can be 0.5, 0.005. Who knows? So M unaffected. So what will happen? Tell me. New equilibrium search. Now first case. Shall I write? Shall I write here? First case. Right. Both are 1. First case. PO2 equilibrium. How much I have written? 10 to the power minus 10 atmosphere. 1 5 activities are pure present there. 10 also. This is first case. Means when no silica added. When no silica added. Tell me quickly. Now, if silica is added, So I will be able to. Tell me. If silica is added, what change will be here? Tell me one by one. Think about this. Like I remove this. Top. Just complete this. This is the last lesson of this topic. If silica, when silica is added, next start the star point. Before addition of silica, when no silica. When silica is added, again write. I'm writing again. Again write. K for the reaction is what? Remember M plus O2. So this you have to follow. I'm writing for you. Activity of M, PO2. Follow what happens. If we add silica, then what will happen? First of all, one by one. Take a equation very cautiously. Very sensitive. These are the terms. Will K change?
No.
Achha, another mental block is silica added, sir, you have not involved the reaction. Okay, you have kept the reaction same. No. See, you can write, presence of silica will be adequately addressed here. If you write silicon plus oxygen is silica, you may write, but silicon is not there. No one is interested. All right. But you can write silica, and silicon also activity will be less than 1. Non-physical. What I'm saying, feel free. Again, still, then silica is where? Yes, now silica will be. Answer me one by one. K, what will happen to K? Which reaction I am considering? M plus O, still these reactions, right? Shall I write? M plus O2 gas is MO2 solid. Otherwise, what I have written? This I am calling K will be affected. No, same temperature, right? Same. So temperature have not changed. I have added silica only, no change in temperature. So K is unchanged. Unchanged, right? This unchanged. Since T is unchanged, since T is constant, T is unchanged. Good boy. Take one by one. Activity of M is what? Activity of M is still there. Still there. MO2 because they have written somewhere 1. This must be any value less than 1. You cannot imagine what it is. If you 10 to the minus 10 or 10 to the less than 0.5, 10 to the power minus 2, minus 3, less than 1. So what will happen to this? So U2 will, so it has decreased. Say ratio, previously compare. It numerator is down.
PO2 will decrease.
So the denominator will down because the both are there. One is unchanged. So PO2 will down. So PO2 will be 10 to the minus 12 atmosphere. Say down to 10 to the minus 10 down. This is the effect of composition. Now, sir, what's the gain, sir? PO2 decreases. So what shall I do? How can PO2 decreases? Suppose what will happen? How can PO2 decreases? Now you have to react perhaps. Otherwise, how it can decrease? So with M, more of M will be oxidized. Silica is a receptacle, is a solvent taking up. More of M is removed. So is it good, sir? More of M removed as? Yes, good. For which? Undesirable. Namely, phosphorus. Silicon. For this, you must. That's why this is called flux. Yes, silica is not good flux. Calcium oxide is a flux. But example, you have this, reduce the activity so that. So the idea is this: reduce the. What is the reaction? Reduce the activity. Reaction move this way. Balance. Reduce this. Then it reduces. It tries to reduce itself also. So that again, re-establish equilibrium constant. So PO2 decreases. So So the reaction moves toward. So the reaction is shifted towards the right hand side, toward the product side, toward the right hand side, right? That is more of M is oxidized, is removed is better term. Phosphorus removal, more of M is removed from the system. If your M is valuable, desirable, don't do this. don't do this. More of M will be removed. You for undesirable thing. Actually, I should have written M. Actually, I should have considered another equilibrium. Okay, this is what I have given him. I tell you what equilibrium should be pertinent to understand this. Practical, metallurgical practical. Phosphorus equilibrium you consider. Since phosphorus is removable in 1. You want more of phosphorus removal. So what you do? Now you can very understand. You're still making half of the class. Okay, but your initial classes are over now. You're still making is coming plus minus maybe. What is this? Phosphorus you want to remove because phosphorus is deleterious, harmful. Okay, for this toughness and all these things, phosphorus. Okay, so phosphorus and sulfur, these two actually harmful. So phosphorus. So you will consider the equilibrium phosphorus. I'm not writing. Yeah, phosphorus plus oxygen is P25. Yeah, P25. So what you will add? Something so that P25 you don't allow it to produce at unit activity. It activities if it is already low, further lowered by adding flux. That is a very good, nice flux, very suitable, universal calcium oxide, lime. Add lime and that will react to it, take up and it is bring it down to very low activity. The moment low activity, what will happen? Phosphorus will be also to the product side and phosphorus removal will take place. But remember, with this addition, it will again establish a equilibrium and let it attain. But by this time, phosphorus has been removed and your how much time?
Sir, approximately 4 minutes.
Oh, stop this. Thank you very much. With this, actually, we stop here this discussion. And the next topic is delta G0 as a function of temperature, delta as a function of temperature, general formulation, general relationship, 5 term that I will take up in the next class. And Illingham diagram still next. These are my plans for the next class, and we will meet later. Thank you very much. Okay, for your cooperation and for your patient hearing. Okay, best audience. Thank you very much.